But yes. I have 4 minutes only? Ah, okay. Very good, thank you. Okay. So it's a pleasure to be here, and I would like to thank the organizers, especially Ilya Grusberg, who I've known for a long time in the old days in Chicago. And so I'm going to speak about actually two subjects which are related to one to the other, but a bit related. So somehow I made the mistake of trying to squeeze two subjects in one talk. So we'll see how things go. I will try to be a bit fast on the first part. This corresponds to the integral mean spectrum for SLE, and then some developments which has been made recently with Eero Saxman and Michel Zinsmeister. The first part of the talk concerns work done with students from Vietnam of Michel Zinsmeister from Orléans, and also some work done with also Michel Zinsmeister and Dimitri Belayev, who is going to be here next week, who is at Oxford at the moment. And so let me start with, some people sadly are not aware of what an integral mean spectrum is. So it's concept of complex analysis in 2 dimensions. And so I just take one example here to fix the ideas, which is the example I'm going to treat later. So it's a whole plane Schramm-Loewenreich evolution. So it's linked with the SLE that Scott talked about this morning. And here it will be, just to be specific, it's a map from the interior of the disk, the unit disk, to the slit complex plane. And so you have a slit, which is a trace of the SLE. It's not very rough, but actually it is a fractal at all scales. And so you map, so here you have 0 maps to 0. It depends on time, so it's a map FT, which depends on time. Maybe I can, so it obeys a certain Loewener equation of this type. So there is depends on time and space, Z. And you have the 2 derivatives. And then you have the source term, lambda of T, which does create the fractality here, which has been actually invented by Schramm in '99, which is here, since we are mapping the interior of the circle to the plane, it's actually a source term which is living on the boundary, which is the exponential of Brown motion. And of course, there is one scale only, which is this famous parameter kappa, as in Scott's talk this morning. And in the case of the whole plane means it's an infinite, semi-infinite curve. And so you have a special boundary condition, which is that when times go to infinity, you should reach the identity map. And if you try to solve that equation as a training for kappa equals 0, so it means lambda is equal to 1 here, try to solve this, you will find out that in time, you will find that an easy solution is what is called the Koebe function, depending in a kind of trivial way of time here. So z over 1 minus z squared, and it's actually a mapping from the interior of the disk to the plane slit by a semi-infinite line. So that is a case where you have no fractality, just it's a semi-infinite curve, so in that case, it will be just a semi-infinite line. There is a concept which is important here, which is when you do this kind of complex analysis, which is to know which part of the plane you map. So here, that was the interior of the plane, of the circle, the disk, to the plane. You have another version, which is some people like also very much, which is the exterior version of the thing. So I write it here, f minus 1 of z, which means the inverse of 1 over f, so the fraction, 1 over f of 1 of z. So actually, it's a mapping from the exterior of the unit disk, so C minus D bar, the closure, so the open set, which is the exterior, to the slit plane. So it's called, so this one was semi-infinite, so it means that if you do this map, it will be a bounded exterior version. So this is unbounded, and this is bounded. And that plays a big role, in particular, when you have conjectures about what is called the universal integral mean spectrum. And that is a version which has been actually studied in particular by Belayev and Smirnov in the thesis of Belayev 10 years ago and published. So I will return to this later. And so what is the integral mean spectrum? So, and something I should say for for you to feel a bit familiar with this kind of process is that when time starts from 0 to infinity, actually you erase the curve progressively. And also there is a point which is along, so there is a source term here, and there is a point here along the boundary which is sent to infinity. So somehow you map the interior of the disk, but you break it somehow to just to open this, to have this curve, to open this semi-infinite curve. So the integral mean spectrum, so it's a concept of complex analysis. So you take a Riemann map here from, say, from the disk to the plane. Usually people like to call it belonging to the what they call the Schlicht set, which is they normalize, you know, with these conditions at 0. But in the integral means is essentially, so you integrate the derivative of your map with some power p, so there are moments of the derivative, of the modulus of derivative, and they are integrated on the circles inside the unit disk at a certain radius r. And the point is, when your map is very rough, very irregular, when you go to the limit, to the boundary of the unit circle, your derivative is going to blow up. And so that integral is going to blow up a certain power of the distance to the boundary when r goes to 1. And of course, it will depend on p. So that it depends on r, p, and p, which is a moment, here a real number. And so if your map is random, which is the case of the SLE, for instance, you would have, you know, different problems like what is the almost sure behavior of this integral, or you can do the simplest thing to start with, which is take expectations of the moment, which is what we do in this case to start with. And then what is the integral mean spectrum? Actually, it's just the way this moment integrated on the circle blows up. So in general, you define the lim sup of the ratio of the logs when r goes to 1 by lower lower values. And if the limit exists, of course, you will essentially see that this moment, this integral means diverges like 1 over 1 minus r to some power. And this function, beta of p, is called the integral mean spectrum. For people who like harmonic measure, there is a relationship between, well-known one, between integral mean spectrum and the harmonic measure. So it's actually related to what is called the multifractal spectrum of the harmonic measure on the boundary of the image domain. So remember, you had your SLE curve. So now you take Brownian motion far away at infinity, and you look at the way they land on the curve with they first land on the curve. That's called the harmonic measure of the curve, of the boundary. So this harmonic measure omega from infinity, so it defines, so you have various points. This is a fractal. It has all kinds of multifractality. This is where the multifractality enters. You have various points along the curve, and they are not the same because they are more or less acute. I mean, they form all kinds of acute angles at all scales. It's more or less acute. And you look at the points where the harmonic measure in a small ball at a point z on the curve out of radius r scales like some power of r. If you're on a straight line, alpha is equal to 1. But if you're on a fractal, this alpha is going to vary. And then you look at the set of points along the curve where you have a certain alpha. And you define f of alpha as a Hausdorff dimension of this subset. So you split your fractal into multifractal subsets, which all have a different behavior under the harmonic measure. And you call the fractal dimension here f of alpha. And then it is well known that actually there is a Legendre transform which relates f of alpha, actually f of alpha over alpha, to beta of p. So you see, and the parameter is really 1 over alpha, and this is just a Legendre transform actually of what is called the packing spectrum, which is really beta minus p plus 1. So if you look at this, in terms of 1 over alpha and f, this is a Legendre transform. So you don't need all the details, just to understand that there is a nice geometric interpretation to those spectra, because by Legendre transforms, they are really giving you the Hausdorff dimension of subsets along the curve. Okay, so let's go back to, so let's make things a little more complicated. There is also what is called the complex integral mean spectrum, where you take, so it's exactly the same slide. So just you take p as a complex number, and you move the modulus. You put it outside. Before I put it inside, now it's outside, and that depends on the complex number now. And actually, it's linked by, again, by Legendre transforms. So there are two components, because there is a real part of P and imaginary part of P. So it means it depends now on two parameters. And it's linked with, by Legendre transform again, with the harmonic measure behavior of the random curve, and also the way it rotates locally. These fractal curves, they have a tendency to, especially when they are conformally invariant, they do conformally invariant curves which are logarithmic spirals. So all of these points locally, they wind indefinitely like spirals, logarithmic spirals. So it describes that kind of spectrum. It's a concept originally introduced by Ilham Binder in his thesis, say, 20 years ago. He's going to be here 2 weeks from now. And let's see, so if the map is random like an SLE, you take, simplest thing to do is to start with is to take expectations. And then, of course, you define the spectrum same way as before, same equations, just lim subs, and hopefully, if it does exist completely, as lim inf2, so you have this kind of behavior. I'm not going to describe that very much today. I'm going to stay with the standard spectrum, probably. And there is something else that we introduced with Michel Zinsmeister and these Vietnamese students, Ho and Lei, which is what we call the generalized integral mean spectrum. So same thing as before, same kind of map. And what we did, we just take mixed moments of the derivative and the map itself. And so now it depends, so P and Q are real, but it depends on two parameters. And again, of course, why not make things complicated when you can? So then, of course, it will depend on two parameters now, and you take expectations if it is random, and then you look at the lim sup if it exists. Well, it does exist, and then if the limit exists, you have this kind of behavior. And then you will have to ask yourself, so what kind of spectrum do I get for the SLE, for instance? But the reason for doing this is actually to treat both. Remember, I told you there were the inner version of the map and the outer version of the map, and they are related one to another by this kind of transform. And this is easy to see. You have it here. So it's a unified treatment of the bounded and unbounded cases, meaning mapping from the interior to the exterior, or map to the plane, or map disk to the plane. Because essentially, I told you one was 1 over phi of 1 over z. Yes? Yes. 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 What will happen that for the harmonic measure, essentially nothing will happen. You will have the same spectrum on the bulk, but this kind of transforms, they are going to involve points at infinity, which play a role in the spectrum. So this is somehow, so in a way, from the beta spectrum, you see a lot of details, but when you look at the harmonic measure, you are going to see essentially the same spectrum for the bulk, but you will have differences at the tips. There will be points at infinity, and there will be different tips too. They were actually, this is one reason to look at that, because actually, as you will see later. So let me go back to this 1 second. So you have, so if I take the derivative, of course, it's related to the derivative of phi with this kind of ratio, meaning that if you are interested in that integral mean spectrum, you end up with the generalized one of the other one. So, and clearly in that case, which will play a role important in the sequel, here in this simple case of the inversion, your Q you have is 2p. That's something which play a role later. Actually, you can, for people who like complex analysis, there are some animals in the zoo which are what they call M-fold transforms, which are making copies of the curves, okay, in the plane. And so you take, this kind of powers with m, and so f of them, m, and then you take the m's root, and you take the right holomorphic branch. You don't need to look at all of the details. Just to say that there are this kind of ways of making copies in complex analysis, and these guys, if you look at their derivative, without looking at the calculation, the derivative at moment p will be linked with the derivative of the original map, but then with a certain power q here. So that's another justification to look at the generalized map, because it gives you access to a lot of standard integral mean spectra from this, in particular for the case of for q equal to, for m equal 1, which was the, you will, m equal minus 1, you will have 2 for S before. Let me, the case of Bela, let me move on. So yes, this is what I'm saying. So you take the standard spectrum is q equals 0. The bounded one, the exterior one is q equal 2p. And then, as I said, you had this relationship. So it means that you are going to so this is q equal 2p. And this is for m positive here. You have all of this spectrum when m goes to infinity. And if you take m negative, then you are going to have this set of blue lines which are converging to the bisectrix. So just an illustration of this tool as an access to various spectra. I'm not going to enter all of these details today. Maybe I should have skipped this. And I want to go back to the whole plane for a minute. So just the same thing as before, same, you know, the Schramm-Loeffner equation and the setting. And so how do you approach a problem? You want to do it rigorously. Don't worry, I'm not going to bring you to the whole details. You try to calculate expectations of some one-point functions, possibly correlation functions. That is also possible to be done, possibly done. And for instance, here in that case, the first thing you would like to do. So again, so I'll go back. This is a Schramm-Loeffner equation. It depends on time. You would like to solve this somehow, and then you take the map at any time because it's kind of invariant. So you take it at time 0, say. So you say this. I take F as a whole plane inner SLE from the interior of the disk. I introduce P and Q as before. And for instance, if you want to have this access to this spectrum, you take the moment of F prime P and F to the Q. But here, I think of F as the whole plane. And actually, if you use, you know, the Schramm-Loeffner equation and you use the technique of martingale, there will be no surprise for many people here that you get differential equations, which are a bit like in CFT, the similar equation when you do a BPZ. BPZ technique here is done with the Ito calculus, and you, for instance, for this these are just moments, but in the complex version. These are the two. You have two copies, one of this guy and the complex conjugate, and these are the moments you are really interested in. These ones are going to depend on Z and Z bar formally, and this one is going to depend on Z only. And you do that, and you find this kind of equation, so a linear equation, but and depending on P and Q, and of course on kappa. And another typical equation which you should get, sorry, for that object, which is the one we are really interested in because we want to extract the spectrum from this kind of term. So don't worry, I'm not going to tell you how you solve it, especially since nobody knows how to solve this. So except that you have two parameters here, you have P and Q, and maybe you are going to find integrable trajectories in the PQ plane. And this is what happens. You do have integrable trajectories. So again, the same expressions. So you take, so I'm taking the simplest one here. You have, in the PQ plane, you have parabolae, in particular, which are floating in this plane, and along which you can actually calculate exactly these expressions. And this is one example, what we call the red parabola, is given by a parameter gamma here. And along that parabola, you have the simple result for F, this expectation, and the simple result for G, which is the one you are interested in. And you see they have this simple structure. You can even disentangle the 2 points. You can say Z is Z1 and Z bar is Z2 bar. So there are two different points, and this is just a correlation function of 2 points. And you see it depends very simply on Z1 and Z bar 2. And then there is a term which mixes them together. And of course, this term is going to blow up because when you take Z1 equal to Z2, this is 1 minus Z bar. And 1 minus Z bar is 1 minus R square. And when R goes to 1, it's going to blow up with this power. So it means you read the integral mean spectrum here in this case directly. But in general, you can't do that. And you have to use other techniques which are kind of standard for these equations. You have to look at what are, upper solution, lower solutions, where this, your operator here, sorry, this kind of operator is either positive or negative. So you have to find approximate solutions near the boundary and, bound from above and below these operators in such a way that you do squeeze these guys in such a way that you are able to read the spectrum. So I'm not going to enter these details. I just want to briefly, let me see, what time is it? Okay, still time. Briefly show you what kind of structure you have in the PQ plane, the plane of moments of the derivative and the map itself. And also surprise that came with this approach. So first of all, these are the parabolas in the QP plane which I mentioned. So each one depends on which kappa you have. So for SLE2, for instance, which is, you have the blue one. For SLE4, you have the red one. And for SLE6, for percolation, you have, when I mean percolation, I mean for the whole plane SLE, which is SLE6, which corresponds to a kind of infinite boundary between, infinite boundary of a cluster in percolation, right? Semi-infinite boundary. And so you have this kind of parabola. And then so the upshot of the result is that what you find that there will be different spectra. There will be spectra which will not depend on Q, the moment of the map itself, and which are the standard spectra, and then you will have another part which will depend on Q. So in a way, and there is only one function which appears in the whole thing which depends on Q, which is given by this formula. So just give it to you here, and I will try to explain what it means. And they are phase transitions. So essentially, this is a PQ plane. Remember, so this is a standard P, so the moment of the derivative. So the standard integral mean spectrum is along this line. And here we just extend it into this plane. And you see that as long as you are not, Q is not negative enough, you have spectra, which I call here, I'm going to describe them in a minute. You have beta naught of P and beta tip of P, which are the standard spectra, they do not depend on Q, which are the standard spectra found in particular by 10 years ago. And but I will return on it later. And then you have a part, so this is, say, in between this line and this purple line and that light purple line and this green, which is a part of parabola. Here, all of these domains called 2, you have the standard spectrum of the bulk. I'm going to describe them in a minute for people who like equation formulae. And then you have another version, which is a tip spectrum, which is also known, which lives in this part above this blue. Actually, it's a quartic, the blue quartic, and this to the left of this purple line. And then you have a certain sector wedge here, where you have a linear spectrum, which is expected somehow for general convexity reasons, but I'm not going to enter these details. So you have a linear spectrum here in this wedge. And here you have a domain below this straight line, D1, below this part of green parabola, and below that quartic, blue quartic, where you expect to have the beta 1 spectrum. The reason for Q being negative is that you have a map which has a point to infinity. So it plays a role in the singularity only when this F, it was 1 over F to the Q, when this F going to infinity plays a role in the divergency. So it means you need to have Q negative. The reason for Q negative here is simply the fact that you have an unbounded map, and you look at the role of infinity in this moment. So, and again, this beta 1 is this one here, depending on 2 parameters. And these ones are depend only on P. What are those? They are these ones. So there are a number of names here. Somehow I derived this by Liouville quantum gravity and KPZ a long time ago. And it was originally for Brownian motion. It was somehow, for the case of Brownian motion, it was part of this very early work of Lawler and Werner. They had these cascade relations which were giving access to this spectra. And then I derived it by Liouville quantum gravity, so totally heuristically. And there was another version by Bettelheim, Ilya Grusberg, Rushkin, and Wigman, I think, by Coulomb gas here. Still heuristic, and actually finally proven rigorously using the same techniques I just described today for the by Belyaev and Smirnov. But actually, as I will explain later, there was actually a gap in the proof, and we repaired it with Dmitry Belyaev and Michel Meisser recently. I will explain why there was a gap briefly. And so these are the three spectra you get. They depend, of course, on, you don't need the formula, of course, depend only on kappa and p. And they correspond to this, tip, beta 0 and beta lin, which are here. Don't need to look at all the details. Just to mention the recent progresses, because that was done in expectation here. And more recently, for the tip, it was done by Johansson, Wiklund, and Lawler. And more recently, even by Gwynn, Miller, and Son for the bulk case, which was pretty difficult. It was done almost surely, not in expectation. And that they are not very different, but the fact is to do it almost surely is much more difficult. And actually, it was only after these people used what is called imaginary geometry, the flow line of the GFF, the coupling between the SLE and the flow lines of the GFF, using that technique that they were able to access the almost sure spectrum, which, by the way, is of course the same beta naught, except for except for outside of certain range when it's linear. So that required a kind of different approach. Could not be done by standard complex analysis. Ilya Binder tried a lot to do that. Smirnov also. And there are also versions which are on the boundary, but somehow you don't need that here. So why was it? So this is kind of spectrum you get. You never saw one. This is one. And this is just the average integral mean spectrum for the bounded version, the result of Belyaev. So this is the one you see. I'm sorry. You see here. So this is beta tip to the left, beta 0, beta lin. Okay? I'm showing this in terms of p now. So I'm following this axis here, except that this is for Belyaev-Smirnov, so it corresponds to the line q equal to p. Remember? I explained to you early on that when you want to have the exterior version, you need to follow q equal to p, which is this line. So actually, if you follow this line, you see only beta lin, beta 0, and beta tip. Okay? On the contrary, if you follow that line, which I'm going to do later, which is the unbounded case, this is the exterior case, which is bounded, and this is the unbounded case. You are going to cross this point here. So I will show that later. It means you have a phase transition here. So let me go back to the standard spectrum for a minute. Okay, so if not seen before integral mean spectrum, this is one. So this is a linear part. This is a beta 0. And then you have this beta tip, which has a slightly different shape. And there are transition points, which are just well understood. So this is for the bounded, yes? Yes? Yes. I know there is a zoo of things. No. Beta of p is not tau of q. No, that's tau of still another one. No. Beta of p is Legendre transform of f of alpha over alpha in the parameter p and 1 over alpha. And tau of q is the Legendre transform of f of alpha in the parameter alpha and f of alpha. So it's different. Yeah, there are three different things. Well, yes, it's no. It's in the p-plane. That's the one that the complex analysts like a lot. The physicists, they like the other ones because they are geometrical. This one, they love it. So I'm following them. So here you have beta tip, beta 0, and the linear part. So again, it's for the bounded case. So it means this is the result of Belyaev and Smirnov for the mapping of the outside of the disk. Now, suppose you look at the unbounded case, which is the mapping from the interior to the outside when you have a semi-infinite curve. You should understand that this curve here, this SLE had two tips. It was a bounded tip, so it was kind of little snake with two tips for this case. And so now if you take the unbounded case, unbounded whole plane, meaning the map from the interior to exterior, you get apparently the same, except that there is, remember, I told you, you were crossing this green parabola, so it means you are entering the beta 1 phase, so where q equals 0, and you had this formula. So actually what happens is actually, so we found out, it was a surprise actually somehow. We found that there was something missing. There was a new spectrum which was lurking behind due to the point at infinity of the map, and which was given by this guy, and actually it was here. So that was the spectrum you would expect, but then suddenly there was this one which was showing up, and while being bigger, and then you will have this new spectrum. Okay, so somehow that was expected, because in a way, when you have a map which has to infinity, something will happen, especially for large p's, which is exactly that. Okay. What do you call? Yes, there is a cusp. That when you go from the bulk to the tip, there is a cusp. Yes. Yes. A spectrum can be like that. Yes, there are things like that, absolutely. It's like a phase transition, like a gas-liquid thing with a Maxwell construction. Yes, same thing. So I'll go back to the diagram. Remember, I know that I've lost a number of people already, but I'm sorry. 5 minutes only? You're sure? Oh. No. 5 minutes? Yes. Yes, miss. Oh, wait. We started at 10. Well, okay, but 10. Even if we start at 10. But if I start at 10. We started at 10. I know. So I have to 4 minutes after 12. Not 9 more. Well, I propose that we dismiss the chairman. I've known him for a long time. We even collaborated. Yes, I know. Yes. Okay, so let me go back. So I know I've lost people, but the first spectrum was for the bounded version outside, so along this Q equal 2p. And the new one is here, and the phase transition we saw is just here. You enter the region where you have beta 1 along this curve, along the straight line here, that's Q equals 0. This is why I put beta 1 of p 0 and kappa. Okay, so that's Q equals 0, and that is the formula here, which corresponds to this, the phase transition. So that was a surprise we found. But then there was another surprise that actually, so let's go back to the exterior case, the bounded case, the case where it was a nice SLE with 2 tips, a little snake with 2 tips. And actually, you were along this curve, so everything looked fine because you never entered the domain of beta 1. Except that that was a green parabola, that was a quartic, and that is the formula you have inside here. Again, the general formula, beta 1 is this one. And what happens, but except that when you go down here, if you zoom below this point, sorry, Q0 here, you zoom below this point, what happens is that you see your Q equal 2p curve, the straight line, which is the one of the exterior case, crossing the green parabola, not the blue quartic. Actually, they are asymptotic to each other. But you cross this parabola, and that parabola was telling you that something happens in the solution of your problem. So it looks like innocent here, because really what happens here is this one. But this is a signal that actually something collapsed in the proof. And if you go back to the paper by Belev and Smirnov, you will find that at some point their solution becomes negative. There is a kind of solution on the boundary of the disk, and such solution has to be positive, and suddenly there is a gap opening, and there is a point where it becomes 0 and then negative. And that happens exactly at that point here. And so it means you have to repair the solution. So the bounded SLE line intersects the continuation of the green parabola at P1, this point here. For P less than P1, the beta 1 spectrum dominates the bulk, but not the tip 1. So what happens here, this is across the bulk and beta 1, the signal of something happening, but the fact that there is a so somehow you still have the beta 1, you will have the tip spectrum, and what happens is really this. So this is a linear path, this is beta 0, The solution I gave before was following the red curve with this inflection point, as you mentioned, right? But what happens that if you look at that was the beta tip here, the red one. And the beta 1 here is just coming from underneath, crossing the bulk spectrum, and stay under the tip 1. So it means that overall, the tip solution is still valid if you have a tip, but if you integrate along the bulk, you are not going to see the tip, you are going to see beta 0, and it means that at some point, you do see this beta 1. And that corresponds to the second tip of this SLE. It was not the same one as the first tip. But the fact is, even so, ultimately, this one still wins. The method actually breaks down, and you have to do something better to actually repair and see that indeed this spectrum, which is the second spectrum, is underneath, and is still. But you can repair the solution. Okay, so I think so that will be okay. So I think I'm going to my analytic continuation, time analytic continuation. And so just to mention the domain of proof, it's not as simple as it looks. So it means we could prove all of these results in this domain here. So it means above this line, above the green line. So in all the upper part, up to this lower branch of the green parabola, there are two up to this red parabola here. So say all of this is under control, rigorous control. But if you follow that line, that line, that line, that line, actually, in all of this domain, for some mysterious reasons, we could not do it rigorously yet. So, but the rest is under control. So anyway, all the phase positions somehow are under control. So I will enter my second subject, which is related to the first one, and linked with the Riemann zeta function. And so I'm going to look at what is known as the universal integral mean spectrum, meaning you take all of your maps from the interior of the circle. Remember that was S, the Schlicht class was the interior map, from the interior of the circle disk to the plane. And now you take them bounded. BD means bounded here. So in particular, not the whole plane SLE, for instance. And you ask what is the supremum, what is the biggest spectrum you could get. So it does exist, and people have studied a lot, and I'm making the story very short here. And there is a famous conjecture called Kretzer conjecture, dating back from the late 90s, that for P real, that spectrum would be given first by P square over 4, so just a branch, a part of a parabola, and then you know a linear part as usual for modulus of P greater than 2. Here, P is a real number. I'm just looking at the standard integral mean spectrum. Okay? It's a very wild conjecture. If you ask complex analysis, they really don't know if it is correct. Kretzer made it with numerical simulations. He also had there were theorems which constrain the possible forms of this spectrum. It's a famous conjecture. If you solve it, showing it is true or false, you probably, if you are under 40, I think that's good. That would be good. So, and it's very, very famous. It's just something which seems unreachable at the moment. There are things known. For instance, it's known that this is correct for P. This part is correct for P greater than 2, and that is due to Pomerenke in 1999. It is also known since the 90s by Carlson and Jones, Carlson-Markarov, I'm sorry, that this formula is also valid for P negative enough, below a certain P naught, which is himself less or equal to -2. So it's known that after -2, somewhere, it becomes like this. There is something well known, which is dated back from 78, that Brennan conjecture, saying that B of -2 is equal to 1. So it's known as Brennan conjecture, which predates Kretzer, but Kretzer is the largest one and the wildest one. And now there is also a conjecture, which was done by Ilya Binder later, which is for the complex case. Remember, I told you there is a complex integral mean spectrum. So this B bounded case for B would be just the same one as this one, just we take the modulus. That's that simple. So, and how does it look? Well, it looks something like that. So you have p square over 4 here, and then you have a linear part, this light blue, and the red. Remember in the spectra I showed you before, we always had a linear part, remember? They all ended with a linear part, all the spectra I showed you. Somehow it's linked with this remark. So as I said, what is known is this. It's all, the way of approach to this point is also known. So there are some rigorous results. And let's see what so the question is, what are the does it exist a function which would have this kind of spectrum? And so the answer is yes, there is one. By the way, I should insist on the fact that this supremum is taken over all univalent functions, meaning they are analytic, and they are injective. That's the key thing. They are not maps which are making a lot of crossings and loops. So this supremum over this class of analytic, bounded in this case, and injective functions. Now, there is a theorem by Makarov, which is actually not very difficult to show, which is if you take now the supremum over all analytic injective functions, not necessarily bounded, then it's going to be the same as the spectrum will be the same as before, but the max of this guy and 3p minus 1. We saw before 3p minus 2q or something. So this is just the spectrum of the Kuber function, of the semi-infinite line. So this is a result by Makarov. And actually, so it means that if Kretzer, say, for instance, is correct, but suppose you have another B bounded here, would be something like that, say, then you would have this 3p minus 1 would show up like this. It's very similar to the phase transition like for whole-plane SLE before, remember? Very similar in spirit. That's the fact that the point at infinity plays a role here. Okay, so what can be added to this in 10 minutes? Oh, I'm sorry. Of course, if you remember, I defined this this generalized integral spectrum depending on f prime and f to the p and q, remember? Depending on 2. So with Astala and Michel-Zinsmeister, we proved an analogous result to Makarov's theorem, meaning that for the generalized, depending on the derivative and the map itself, you have this usual case and then just this supremum. So it means if I go back to the phase diagram I had before, this would be the phase diagram for the Kretzer conjecture, meaning you would have minus p minus 1, p square over 4 here, exactly like before. That would be what you would have, p minus 1 here in the sector here, and here a certain green parabola again, where underneath which, and here a straight line, there was a quartic, now it's a straight line, and under this straight line and this one, you have this Kuber function spectrum. So if Kretzer is not correct, you would have a different thing here. You'd have here low enough this one by Carlson-Makarov, but essentially you would have this structure. And here you would have exactly this would be correct here because we know that here, so that would be correct. Okay, let me just so I'm going to go to the Riemann zeta function. There are a number of people who, No, 3 minutes, Yvon. It was you had 4 minutes more, and this is still 3 minutes to noon. 7 minutes. No, we started at 14, and it's 4 to 2. Sorry, I forgot that. Okay, so I stop. It's too bad. Too bad. Okay, I will be. Okay, so maybe no questions. So the data function. He made me lose my control by providing fake information. So you all know that, the Riemann zeta function, defined like this in particular for real of S greater than 1, analytic continuation. Riemann conjecture, you all know that the zeros are on this critical line. And there is a randomized version, which is quite important in this talk, which is this version where you put some extra phase factors. These are all the p's here are primes in this part of the talk. Before it was a moment, now they are primes. So this is just the Euler product, and then you put a phase. For each p, you put a different phase. They are all IID, and independent one of each other for different p's, and they are uniform random variable on 0, 1. So you move along the circle. For real of S 1/2, this guy becomes a generalized function. Actually, it's a distribution very similar to the GFF on a line. Okay, so I'm not going to use that very much, not here. And then there is so this is useful because if you look at the values, I'm sorry, I have to rush a bit silly, but if you take log of this zeta function on this famous critical axis, you put yourself far away. Tau is big. It's between t and 2t when t goes to infinity. You are far away up in the upper half plane along the critical line. And then you look at what happens when you zoom. After tau, you zoom on a small interval, say h of order 0, 1. It has been, people who know about the Riemann zeta, they know why people look at that now. And then a good model of this log of the modulus is actually this process. You take this guy and you take the first term of the expansion, and you look at the real part of the sum over p up to a certain t. So because that, if you let p goes to infinity, this is not going to be converging. It will be a generalized function. But if you remember, I am the critical axis here, and then you put these random phases, you take the real part. This is a good approximation of this. And these guys are log correlated, of course. And so it means that in the Euler product, somehow, this large tau, which is here, which is large, actually, when p varies, just is mimicked by this random phase here. OK, let me move on. This is exactly, so it's a courtesy from Louis-Pierre Arguin. This is how the minus the log of zeta moves when you are far away. You are at t equal 10 to the 4. And here you look at an interval of 0.50, okay, here between 10 and 50. And each time there is a 0, your log goes up to infinity. So it looks like a random function, which it is. And actually, of course, it has many mysterious properties, but essentially this kind of process we have in mind. And here I just put this slide to show that, of course, there are many recent results for zeta or the randomized version on the critical line for the moments, the maxima, the relation to Derrida's REM, the multiplicative chaos, and of course there is this paper a long while ago, numerical paper by Fyodorov, Yari, and Keating, and also all of these works, which I don't have time to describe, but there are a number of people in the room who are here. So Kissler is here, and Najnudal is here, and Fyodorov is here, and so on. I hope I don't forget somebody. No. And so there are important objects which are the moments. So here, this is the moment of the modulus of zeta to some power gamma. So of course, if that would be a derivative, that would be like a moment of moment which you use for integral mean spectrum. Here on a line, but that's essentially the same thing. So here you integrate over h, and you keep tau large but fixed. So these are the moments with gamma positive. You have the random version also. Remember, this xt is a bit complex, but you had this random version of the log, so which is just a truncation of this guy here, of the log of this guy, of the modulus, sorry. So you can take, so if you want to mimic this for the randomized version, you can also define this as the exponential of gamma xt. Remember, this x was a log, so it's like a moment. And of course, that looks like GMC, a bit, at least formally. Except that we have a remember, this is a regulator. It means you sum over primes up to t only. And h is just the place where you look at your process. And so for the randomized version, people have been able, so you look at the quench free energy, so you take the expectation of the log. So like a free energy. So explicitly this guy. And then there is a theorem by Arguin and Tai, nice paper, where they show that the limit when t goes to 0 of ft over log t is just a convergence to a certain function, which is gamma square over 4 and f of gamma minus 1, which of course is related to something that many of you know,
But before I go to that, there is a stronger version of it, a recent paper by Arguin, Ouimet, and Radziwill of the beginning of this year, where they show that for almost all tau, meaning all of this interval minus a subset, not of measure 0, but of measure less than linear in t. Okay. That's why I put almost here between quotes. So for essentially all of this interval minus a smaller set, the moment, remember, I'm sorry, I'm going a bit fast, but the moment was this guy. For the actual zeta, okay, this guy, when tau is large, this guy is going to essentially scale like log of t, like here, log of t to this power plus petit tau of 1. Okay, so that's a result by Arguin, Ouimet, and Radziwill. And of course, for people who are familiar with the REM, and written in a certain way here, this f of gamma here, if you set gamma equal to beta, where now beta will be your inverse temperature, for people who like statistical mechanics, if you do that, this function is minus beta f of the REM minus 1, where so my friend Derrida, Bernard Derrida, so this free energy of the REM is, as usual, in the proper units, minus 1 over beta minus beta, or minus 2, when you have freezing. So that, of course, was looked at actually by Fyodorov, Yari, and Keating numerically, and somehow this result, right? Yeah, you had a nice curve where you see that. That's right. So that somehow is a rigorous approach to it, right? Okay, so this is a state of, so remember, all of this was done on the, I'm sorry, I should have to go back, on the critical axis, zeta of 1/2, okay? And here, you had p to the 1/2, meaning you were on the critical axis. And so I will, so now I want to go off. So this was the result I showed. I think I have only 2 transparencies. Yes. And so you move off the critical axis. So you take sigma greater than 1/2. This is just where all the salt of the story is. So you take your approximation of the random one. Sorry, of the random one. So instead of having p to the 1/2, you put p to the sigma. You move off. Now you can sum up to infinity because it does converge. So you no longer have this capital T, right, capital T. So you take your theta p ID as before. So this is a random process, and you define. So before if you really want to go back to zeta, you take this. You take the moment on zeta, but off the critical axis, right? Or you consider the random version, this one. Then you take this one, which you represent by this guy. So let's say for today, I just do this one. Forget about the zeta. So you look at this guy, this moment here, but now you're off critical axis, right? And so you represent by this exponential. You try, and then you calculate again the current free energy, but now for a regulator sigma, as before, and you show that indeed this guy, exactly like before, scales has a limit, which is given by the REM free energy. But instead of having log of t, you have now log of sigma minus 1/2 minus 1/2. And if that is correct with this formula, and that actually and this is your moment, it means that if this is a derivative of the primitive, this is an integral mean spectrum. So you have found a function, actually the primitive of this guy, which has a Kretzer conjecture as a spectrum from this. This shows you that you have Kretzer here, right? So this is a Kretzer integral mean spectrum of the primitive of the random function. And so similarly for zeta, you can do it also in principle. So let me just conclude, but I would like to tell you that we did not solve the Kretzer conjecture because, so the proof, I just skip the details, but the Kretzer conjecture concerns univalent injective bounded functions. So here you have, the problem is the injectivity. And actually we have this set proposition with Saxman, and that if I take this primitive, if I take a little square which is to the left of the critical line, then almost surely phi is not injective on this. So, and we show it by showing that this this guy should be bounded, and we show that it goes to infinity. I'm finished. Sorry.